So in this section, I'm going to be trying to give you a better feel for what structures look like when solutions can be formed. And this really relates to intermolecular forces. And so what I've done on the slide is I've listed the kinds of intermolecular forces that we introduced in the last chapter. And I've listed them from weakest to strongest. And there's the induced dipoles or dispersion forces. There's dipole-dipole interactions, hydrogen bonding, and ion dipole forces. And these tend to be the strongest, and these tend to be the weakest. Now, just by reference, something that's important to know is if you have CH in your structure, so let's say CH3, CH2, none of the CH bonds are polar. There are electronegativity differences at 0.4. So these regions represent nonpolar. On the other hand, anytime you see OH, right, that's going to be with a nonmetal on this side. So let's say another carbon, so a CH2. Right? This is always going to be hydrogen bonding. And they're also polar. They have to be because the oxygen-hydrogen bond is polar, and the oxygen structure is not symmetric. And then anytime you see in organic compounds, anytime you see carbon bonded to nitrogen or carbon bonded to oxygen or any other element really, this will lead to a polar part of the structure. So these kinds of bonds are always polar. So that's just sort of a general reference to help you place things in terms of this scale. So when we're looking at a structure, we'll be able to quickly determine whether or not segments of it are polar or whether or not segments of it are nonpolar. So what your book lists is it shows a set of intermolecular forces, and these can either contribute or oppose to the formation of solution, and it has to do with the energetics that we talked about earlier. And you'll notice this is heptane C7H16 and pentane C5H12. These are all nonpolar. So the only thing, because they only have CH bonds, right? So the only thing that can be true in terms of intermolecular forces, they have dispersion forces, and these are the weakest types of intermolecular forces. Now, the thing that happens in dispersion forces, though, is as the molecule gets longer, the net exertion of dispersion forces, the force gets bigger because it happens at every point the molecule can make contact. Now, molecules like acetone, the oxygen, and there's bonded to a carbon, or chloroform with carbon bonded to 3 chlorines, these molecules are polar, and these are a force of attraction between the molecules. And we have hydrogen bonding, for example, between ethanol and water, so that's OH bonds. And we also have ion dipole interactions, which are the strongest interactions that we talk about in the formations of solutions. So rather than just sort of point at these pictures, I wanted to show you how these molecules will interact with each other. And what I chose to do is to show the interactions between heptane molecules and then also the interactions of water molecules, and then what happens when you mix them together. So let me explain to you what you're seeing here. This is a number of heptane molecules. So each one of these has 6 carbons, or 7 carbons, and 16 hydrogens. And what I've just done is done a simulation to sort of get their shape to be exactly right. And now what I'm doing is I'm allowing the intermolecular forces of the molecules to act on each other. So what you'll see is that heptane molecules are attracted to each other. You notice how they're starting to cluster. Even though they only have weak dispersion forces, right, that's enough to keep them together. What we're going to do here in the next short segment is show what it looks like when you do the same thing with water molecules. So the same thing, I'm going to allow their structures to sort of stabilize, get their best shape. You'll notice it added lone pairs. There were no lone pairs on the heptane, and now I'm going to allow them to interact with each other. And again, you'll notice that the water molecules have strong intermolecular forces for each other. You notice how well they're clustered together, and none of them are breaking apart. So, strong hydrogen bonding, strong intermolecular forces of attraction, right? Now what we'll do is look at a mixture. So I'm going to minimize again. I wanted to show you that this is 2 layers thick now, so there's a lot of molecules in here. And I'm going to minimize the energy is what they call it. When you minimize the energy, you allow the molecules to individually come to their best sort of shape. And now what we're going to do is we're going to run the simulation to see what happens when we allow the molecules to interact with each other. So if we can zoom in a little bit, what you see is still the water molecules like to stay clustered to each other. And the heptane molecules are also staying clustered. And this happens because the nature of the intermolecular forces are so different. The polar hydrogen bonding molecules of water tend to stay clustered with each other because of their strong intermolecular forces and then separate themselves from the heptane. Now the heptane is not without intermolecular forces, and so they stay clustered together as well. You'll notice in the region on the right side in the middle we have a large cluster of water molecules. In the bottom left the water molecules remain clustered, and in the top those molecules also stayed clustered together. And we have a couple of different separate populations of heptane. So again, the nature of the intermolecular forces is important in whether or not solutions will form. When you have heptane and water, because their intermolecular forces are so different, they tend to separate from each other. So when you make an oil and vinegar salad dressing, this is what you see when the water and the oil tend to separate and you have to remix them all the time. So one of the important things to talk about is the nature of the different solvents that get used in laboratories. In Chem 1A and Chem 1B, we generally deal with water as the solvent. And water is a very strongly polar solvent and hydrogen bonding, so it has a tendency to be really good at dissolving polar substances, ionic substances, and things like that. And that works well because we tend to deal with a lot of ionic compounds in Chem 1A and Chem 1B. So solvents are categorized by their polarity. We have polar solvents, good at dissolving polar substances in general. And then we have nonpolar solvents that are generally good at dissolving nonpolar substances. In general, although it's not 100%, but in general, polar solvents and nonpolar solvents tend to be immiscible. That is, when you mix them together, they'll form layers depending on their density, with the more dense substance being at the bottom. Now, if you look at a list, and there are extensive lists of polar and nonpolar solvents, and they're sorted many different ways, but this is a very simple list. It shows water, acetone, methanol, and ethanol. So these are alcohols and they're hydrogen bonding, so that puts them in the polar solvent category. And then there's water, which of course is polar, and then acetone, which has some organic, some CH nature to it, but also has a C double bond to O here, which makes it polar. So these are generally considered to be polar solvents. Now, diethyl ether, right, and hexane and toluene and carbon tetrachloride are all nonpolar solvents. Now, diethyl ether has an oxygen in the middle, and you know what I said previously about structure, right? If it has a CO bond, it tends to be polar. But in diethyl ether, the oxygen is placed symmetrically between the carbons, and it tends to have less polarity because of that. If you notice, it has here, it says diethyl ether has a small dipole moment and can considered to be intermediate between polar and nonpolar. So this is one that dissolves a little bit in water, right, but doesn't make a very good solution with water. Usually forms separate layers if you have the right quantities. But hexane, toluene, and carbon tetrachloride are completely immiscible. So if you're trying to dissolve something that's polar, you pick a polar solvent. If you're trying to pick something that's nonpolar, you pick a nonpolar solvent. Now, polarity is not completely a cut and dry thing. Okay, it's not 100% guarantee for it to be a polar solvent. So take a look at this. What we have is a list of 5 different alcohols with 1 carbon to 5 carbons, okay? And we've listed the solubility in water per 100 grams of water and the solubility in hexane per 100 grams of hexane. So you'll notice that methanol is miscible in water. So it has a small hydrocarbon portion, the CH here, right? And the polar hydrogen bonding alcohol functional group. So that's what makes it miscible with water. If you take ethanol, it has 2 carbons, right? This is still miscible, but notice what happens when you get to the 4th carbon. All of a sudden, the nonpolar portion, right, tends to separate the alcohol from the water. And the water tends not to be able to dissolve the butanol very well because it only has a small polar hydrogen bonding portion on it. The larger the number of carbons gets, the less soluble it gets. On the other hand, if you look at the solubility in hexane, you can get very little methanol dissolved in hexane. And that's because the polar nature of the methanol tends to keep it from forming a solution with the hexane. But as soon as you get to 2 carbons, all of a sudden all these alcohols become miscible. That is, you can mix them in any proportion. So it's not completely cut and dry about solvents either because of this. If you have something of intermediate polarity, you have a better chance of dissolving it in one of these alcohols, or if you have something of low polarity, it's probably a good chance you could get it to dissolve in one of these alcohols or maybe hexane, depending on the type of solvent, the properties you need of the solvent. So again, solubility depends on structure. Polar substances and polar solvents tend to dissolve polar substances, right? And then nonpolar solvents or substances tend to dissolve nonpolar, but there are degrees to which that can occur. And so the more hydrocarbon-like the structure becomes, the less likely it is to be able to dissolve something that's polar, but the less hydrocarbon portion, the more hydrogen bonding portion as a percentage, the more likely you'll be able to dissolve a polar substance. So I want to show you a couple old videos that I've kept over the years. I think they're instructive. This is oil and water, right? So actually it's vegetable oil sitting on the top and water at the bottom because the vegetable oil is actually less dense than the water. And let's look what happens when you try to mix.
Why don't oil and water mix? The hydrogen bonds between water molecules are too strong to be broken in order to produce a relatively weak interaction between water and the molecules in the oil. Thus, water excludes oil from entering the aqueous phase.
So if you could imagine back to the video we saw with the molecular simulations, right? You shake it up and you can mix them up temporarily, but the water molecules have such strong intermolecular attractions for each other, they tend to pull themselves apart. And when you have a large amount of water, it tends to form a layer at the bottom. Now, this is an interesting video for a number of reasons. There's a small amount of iodine in the bottom, and they try to dissolve it into water. And water is our polar solvent, right? And then carbon tetrachloride, if you go back to the chart here, carbon tetrachloride is our nonpolar solvent. So if you dissolve the iodine first in the water and then you take the carbon tetrachloride and you add it in, this is what happens.
Solid iodine is not very soluble in water. If the dense, nonpolar solvent carbon tetrachloride is added to the mixture,
So it goes to the bottom.
it forms a layer underneath the water. The nonpolar iodine is extracted from the water and readily dissolves in the carbon tetrachloride. The difference in color between the two solvents indicates that the iodine molecules interact somewhat differently with the solvents.
So what happened was there was a little bit of iodine in here, and they added the carbon tetrachloride, which was more dense. It goes to the bottom. And two things are happening. More iodine can dissolve in the carbon tetrachloride than the water. That's the intensity of the color in part. But also, because iodine is more soluble in the carbon tetrachloride actually has the ability to remove the iodine from the water and extract it. It's called an extraction into the carbon tetrachloride layer. This is the way like natural essences can be extracted from plants. So if you want to, for example, extract mint oil from mint leaves, you can actually use something like ethanol. It turns out the mint oil will be more soluble than the ethanol because it's an oil, right? So it's relatively nonpolar. And it can be extracted into the uh, ethanol more efficiently than it can be extracted by water. And so it essentially extracts the essential oil into the ethanol. And then the ethanol, because it has a relatively low boiling point, can be evaporated off, leaving you with the concentrated oil. So that's often the way it's done.